All right, some of the homework, you need some additional information. That is, you need to know something about platinum platinum complexes that you can look up in the book. When you start looking through the book, back in, I don't know what chapter that was, but 2 plus or 4 plus, right, are the common charges for platinum. So that's number one. Number two, you start looking through the chapter and you look for certain patterns. One of the patterns that you're going to see is that 2 plus tend to be square, planar, and that the 4 plus compounds are octahedral. In other words, the 2 plus are just coordination number 4. Those are 4 bonded atoms. And the 4 plus tend to be coordination number 6. And so with this additional information, we could figure out, which charge belongs to which, because, what was it? It was the tetra-aqua. Okay, if we have the tetra-aqua complex of this, it's 4 coordinate, and what do you predict? Yeah, it's most likely 2 plus based on what we've seen in the book. And then the other complex is the hexachloro. Okay, hexachloro is most likely the 4 plus. Now, the thing is, if this were 2 plus, what would make the charge on this ion? 4 minus. Now, is a 4 minus ion something that's common? No. It's a little bit too high in the charge. As the charge builds higher and higher, you reach this point where it's like trying to build up static electricity. You're going to reach a certain point where it's just going to discharge. The static electricity, you can't build up too high of static electricity. And the same thing, the charge is something's going to happen when the charge gets too big. It's going to cost too much energy or something else. But anyway, so this makes sense that this were 4 plus and this is a 2 plus. Now, this could have been a 4 plus here, but 4 coordinate. All right, so where does that come from? That comes from looking at the complexes in the chapter, the platinum ones in particular. All right, other questions?
Are you going to post the practice exam? That'll be difficult, just kidding.
Okay, yeah. I'm going to post, I tried to post the practice exam for chapter 15 over the weekend. But my computer with all of my files on it is dead. And so I lost those, so I'm trying to recover some files right now with chapter 15. But chapter 15, you don't want to neglect that because we're starting chapter 16 now. So you want to stay current, or try to stay current with the chapter 15 material too, because you have this extra time for chapter 24.
Professor?
Yeah.
For the test tomorrow, do we have any drawings?
If you had a drawing, it'd be a simple drawing.
Isn't the homework very extensive?
Yeah.
No, you wouldn't be required to draw anything like that. Like what we did on the board. What I did on the board. Do the drawings make sense? What did I do on the board? Let's take a look at your notes. That's it. Should all be in your notes, right? I know, Adrian, your notes are. Please just review through those. Usually when you study for a test, what do you do? Okay, what was the most important drawing that we covered? Would you say? What do you think is the most important drawing? No, not hexaqua. The most important drawing that we covered was the Lewis acid-base reaction. We talked about that. I mean, all these are the same mechanism. Mechanism exactly the same, so you just learn one drawing, you can figure out the rest. Right? Now, memorizing the shapes of the ligands, no. You don't have to memorize certain structures for that. There isn't that much drawing on this test. The drawing is primarily going to be on the second test for chapter 24, and that's when we talk about isomers. And there you're going to have to draw. In fact, you're going to have to draw the cis, trans, and then they have something called the mirror, face, and then they have something called optical isomers or stereoisomers. You'll have to draw those. Although cis-trans. Well, anyway, don't worry too much about the drawing, but you should know something about how these react. Okay, anything else from chapter 24? Okay, we're going to start chapter 16 now. Acids and bases, part one. All we're going to do is we're going to look at base in water and an acid in water. That's it. Acid and water. Seems like a simple mixture, but it isn't really so simple. I mean, the most complicated mixture we're doing acid and water. But there's a lot happening because water has its own equilibrium and an acid has its own equilibrium. And so there's actually two equilibrium going on or more, because not only do you have monoprotic acids, you also have diprotic and triprotic acids. And so, the acid, we're looking at, monoprotic, diprotic, triprotic acids. Well, if you have a triprotic acid, then, it's 3 acidic hydrogens you got to worry about, all the equilibria that's happening there. And then water itself has something called autoionization. And so you have another equilibrium there. And so water autoionization we call KW. W stands for water. And so we got this equilibrium here. And then monoprotic, we have a Ka. A diprotic, we have a Ka1 and a Ka2. And a triprotic, we have a Ka1, Ka2, and a Ka3. And so for something like a triprotic acid, we got 3 equilibria happening. We got these 3, actually more than 3, because we got these 3 plus what's happening with water. Now, do these equilibria act independently of one another? And the answer is no. They all interact with each other, so how do you deal with this? 4 different equilibria happening at the same time. And so chapter 16 gets a bit more complicated than something like chapter 15. Chapter 15, we're only dealing with one equilibria, and it gets easier too, because in chapter 16 we're never going to go beyond a quadratic. In fact, everything ends up being a quadratic in chapter 16. We don't have any 3rd order, 4th order, 5th order, 6th order ones that we have to deal with. And so in a sense it gets more complicated, a lot more complicated because of all this that's going on. In another sense it's easier because the math is a little easier to deal with than chapter 15. And so let's first look at just pure water and just try to understand pure water equilibrium. If we have pure water, then let's say pure water at 25 degrees C. What do you visualize when you think of pure water at 25 degrees C? 25 degrees C, why 25 degrees C? Because most everything we're going to be dealing with will be 25 degrees C, because that's what we call room temperature. It's not standard temperature. There's no standard temperature. It's just room temperature. It's there's a standard temperature for gases, but that's only for gases. And what is that? No, 0 degrees C. 0 degrees C. We aren't going to be doing too much aqueous chemistry at 0 degrees C because everything will be frozen or close to frozen. So, because water should freeze at 0. So we don't want to use that temperature. 25 is a good temperature. At 0 degrees C, what's happening? What do you visualize? You got a block of ice there. What do you see in that block of ice? It has a fairly open structure. You guys remember the crystal structure of ice is expanded. Its solid state is less dense than its liquid state, so there's lots of void spaces in there. The void spaces are there to orient the water molecules such that the hydrogen bonding interactions are maximized. And then when you warm up that block of ice, what happens? Can you just visualize it in your mind? What happens to the... Well, what do you have going? At 0 degrees C, is there any motion? There's no motion? There is actually motion. There's vibrational motion, and maybe, but I doubt it, in a block of ice there shouldn't be any rotational motion, and definitely no translational. In some weird solids there's actually rotational motion, but those are more spherical. Like you have a spherical molecule trapped in the solid, it can rotate. But water molecules, in order for them to rotate, you'd have to break the hydrogen bonding interaction, which required so much space to begin with. So that wouldn't happen. So you just have rotational motion. No, vibrational. And then what happens when you warm it up? You start breaking those hydrogen bonding interactions. You still have hydrogen bonding interactions because that's what holds the water molecules together, but they aren't oriented to maximize the interaction, minimize the energy of interaction. And so you start breaking them up, and then you introduce rotational and translational motion. And then you keep heating up to 25 degrees C, and you're just going to increase the, what we call kinetic energy, which is energy of motion, right? And so you're just going to introduce more motion. And so now we've heated up, we warmed it up to 25 degrees C. What do you see? Now we have water molecules rotating, vibrating, and translating in here. But are they all rotating, vibrating, and translating at the same energy? No. You'd see that some are kind of slow and some are kind of fast, right? But the bulk of them are going to have some kind of average energy. Which, that average kinetic energy is directly proportional to the temperature. You guys remember that from kinetic molecular theory of gases? Well, it's the same with liquids. The temperature is directly proportional to the average kinetic energy, but the average is just the average kinetic energy. What we're actually going to see is something called a distribution of kinetic energy. Right? And what does that distribution of kinetic energies look like?
Almost like a bell curve.
Yeah.
Like a tail.
We plot kinetic energy on the x-axis, and then what do we plot on the y in this distribution curve? Somebody remind me what we plot on the y. Not the speed, not the temperature. Temperature is fixed at 25. All of them, this is 25 degrees C. Percentage? It could be percentage. Percentage of what? Percentage of molecules? Yeah. Or population. If we normalize it to 100%, then it's percentage. Normally, you can either normalize it to 100% or you just say population. Just retain. And so we're going to get a curve like this. Does this curve look familiar? Yeah. So even though the water molecules are 25 degrees C, there's going to be some fraction of water molecules that are going to have quite high energy. It's a very small fraction, though, correct? There's a very small fraction of water molecules that have considerable energy. let's have a threshold energy here. This is enough energy to break bonds. Yeah. And so if you have water molecules with this high of energy, when they collide with each other, bonds can be broken, new bonds can be formed. And we call that, let's say enough energy to cause reaction. When we break bonds and form new bonds, it's a chemical reaction. Cause reaction between water molecules. And so let's look at it. Most collisions, two water molecules come together and collide. Most collisions are going to result in no reaction. They just bounce off each other, right? But let's say we're dealing with that small fraction there. So most water molecules aren't going to collide. So we'll draw it with these uneven arrows. This is not to indicate the reverse rate is faster. It's just to indicate that the reactant side is more favored than the product side. But this tiny fraction here, which will indicate with a small arrow here, this tiny fraction is energetic enough to collide. And what we get is an acid-base reaction. This would be the base, protons donated. This is a Bronsted acid-base reaction. This is called the autoionization of water. Here. Well, we could determine how much. Do we worry about liquids in an ice table? No, we don't. In an ice table, we have something like this, right? Ice. And let's fill it in, the ice table. And so we got some hydronium ion concentrations, initial, hydroxide ion concentrations, initial. And the way we visualize this is like this. Do you know how much initially there is? No. And so we mentally do this. We reset all the atoms to the left. And so we reset that, and then we start at 0 and 0. And so essentially we're resetting all the atoms to the left so that there's nothing here. And then, okay, let it react. This is all mental because the reaction, can you stop this reaction from occurring? The reaction's happening right now as we speak. There are some water molecules in here that are energetic enough to actually react. Now, how many are there? Well, so we do a change. What's the change going to be? Plus X molar, plus X molar. So at equilibrium, we should have X molar and X molar. So we do two things. We could either figure out what X is if we know what K is, right? Or we could just experimentally measure one of these. If we measure, do we have to measure both of them? No, because they're related by a 1-to-1 stoichiometric ratio. And so we can measure this. Do you know how to measure hydronium ion concentration in water? pH, right? And so we take a pH meter and stick it in the water. And so the pH comes out to 7.00. Should. I know if you did it last semester, it didn't. It was more like 5 or 4.5 or something like that. But that was because it was not pure water. Pure water should be pH 7.00 at 25 degrees C. What do you think if I change the temperature? If I change the temperature, do you think the pH will change or the pH will stay the same? This is a trick question. Will the pH change or will the pH stay the same? It should change. It should change because what happens when you increase the temperature? This shifts to the right? And you're going to have more reaction, which means a higher hydronium ion concentration. So at high temperatures, we expect more hydronium. And this is weird because this is an inverse relationship. So if there's more hydronium, the pH can go up or the pH will go down. The pH goes down. And so at higher temperatures, the pH should go down. At lower temperatures, the pH should go up. Just at 25 degrees C, the pH should equal 7. I said it's a trick question. It's a trick question because who wants to figure out the pH at every temperature? Nobody. And so what modern pH meters do is they automatically adjust for temperature. And so no matter what the temperature is, it'll recalibrate itself so it's always reading 7. Okay. And so that's why it's a trick question, because a pH meter does not, when you take a pH reading, water should be pH 7 at all temperatures. Okay. But in reality it's not. It's just electronic adjustment. That will do it. Because, how often do you set the thermostat in the lab at 25 degrees C and it just stays there stable throughout the whole lab period? Never. I think. In our lab. What's that? Because the pH meter is only sensitive to the hydronium ion. And so the pH meter doesn't care what the hydroxide ion is doing. pH is just measuring the hydronium. Now, if we want to define what a neutral solution is, a neutral solution technically isn't pH 7. You know what a neutral solution is? This is a definition that holds true at any temperature. Because what happens if the pH drops a little bit? Does the water become more acidic, or does the water stay neutral? It's just pure water. If the pH drops as the temperature increases, does the water become more acidic, i.e. lower pH, or does it stay neutral? It stays neutral because you know the definition of neutral. What is the definition of neutral? The definition of neutral is not pH 7. The definition of neutral is equal concentrations of hydronium and hydroxide. This holds at any temperature. And so pH neutral is defined as the hydronium ion concentration is exactly the same as the hydroxide ion concentration. And therefore, regardless of the temperature, as long as that holds true, then we're dealing with the neutral substance, i.e. water. Right? And so this can change, the hydronium goes up, so does the hydroxide. It's a 1-to-1 mole ratio. If the hydronium goes down, so does the hydroxide, 1-to-1. Anyway, what we can do is, P is called a power function. So let's just review the power function very quick. pH is the negative log of the hydronium ion concentration or the hydrogen ion concentration. And so this is what the power function is. Okay? But it's really not the power function. It's a negative power function, we should say, because of that inverse relationship. This is negative here. So, negative power. That is, if we use the property of logs, the hydronium ion concentration is 10 to the minus pH. So the pH is the power of the hydronium ion concentration here, but it's a negative power of the hydronium ion concentration. That's what it is. And so the pH is 10 to the minus 7.00. But in power functions, power functions are kind of interesting how we do the sig figs. So if we have a pH of 7.00, how many sig figs is that? 2 sig figs, actually, because the 7 doesn't count. They're only 2 sig figs. And so the numbers, the key is the decimal. The numbers preceding the decimal are not significant. It's the numbers after the decimal that are significant. And the reason is because it's a placeholder. And so there are actually only 2 sig figs. So the way we write this is 1.00 times 10 to the negative, oops, sig figs. I got 2 sig figs. 1.0 times 10 to the negative 7. And so do you see the 7 is just a placeholder because that means I need 7 decimal places. Yeah. And so 1, 2, 3, 4, 5, 6, 7. See? And so the 7 is a placeholder. It's not really part of the number other than telling you how far to move the decimal place. And so this is why it's not significant. Does that make sense? Whereas the numbers after the decimal tell you the number. That's right on. So, we do this experimentally, we can measure this, and it comes out to 1.0 times 10 to the minus 7 molar. If we know the hydronium, then we know the hydroxide. The hydroxide's got to be 1.0 times 10 to the minus 7 molar. And therefore, K for this, which we call Kw, is equal to the hydronium ion concentration at equilibrium times the hydroxide ion concentration at equilibrium. And this is going to equal 1.0 times 10 to the minus 7 and 1.0 times 10 to the minus 7, which gives me 1.0 times 10 to the negative 14. Now, the K's have to be associated with the temperature. This is at 25 degrees C. Does K change with temperature? Yes. Now, tell me what happens to this K. As the temperature increases, will Kw increase, decrease, or stay the same? Increase. Good. And so as temperature increases, Kw is expected to increase because we're going to have more collisions. Now this is a dynamic equilibrium because, you know, hydronium hydroxide, is that a stable acid-base combination? No, it's very reactive because it's a strong acid and strong base. So as immediately when these form, they can react and go back to two waters, right? And so immediately when I form this, shouldn't it react, neutralize itself, and go back to water and then stop? Doesn't it just stop? Let's say I form this and that's it. I got hydronium hydroxide, 1 times 10 to the minus 7 plus 1 times 10 to the minus 7 goes back and forms a little bit of water. Yeah? And so this should go to 0 as this reacts. As this reacts, it should go back down to 0 because I consume all my hydronium and hydroxide, strong acid, strong base neutralization. Yes? No, why not? It's an equilibrium, but why doesn't it? Why doesn't this is such a favored reaction? In Chem 1A, you'd say there's a very strong driving force for this, going from stronger acid to weaker acid, stronger base to weaker base. There's a big driving force for this reaction that way. That way. And so if I look at that, that's a huge driving force. Hydronium and hydroxide should completely react and neutralize. This should self-neutralize each other back down to 0. And the answer is it doesn't. It doesn't. Well, if you say it's equilibrium, that doesn't really explain it. Explain it in a more fundamental, theoretical way.
There's still molecules that pass that threshold of energy.
Yeah, right. You can't. The thing is, you know, sure, it's going to react, go down to 0, but what's going to happen? You can't stop. Can you stop these collisions? No, I mean, the water's at 25 degrees C. You can't do anything about that. It's going to collide and continue to produce it. the concentration can't get too high. You know why the concentration can't get too high? Well, you know, if I got these collisions, why doesn't the concentration just keep building up and building up and building up bigger and bigger?
They do neutralize.
Right, because this is the whole idea of the dynamic equilibrium, right? As the concentration of the product builds up, you're going to reach a point where the rate of the reverse reaction is equal to the rate of the forward reaction, and then we've hit the point of dynamic equilibrium. And so this is going to be maintained as a steady state concentration, even though it's constantly cycling, you know, but you're always going to have this because of the collisions. And so this is the equilibrium that's happening in water. Now in this chapter, we're going to add some acids and then try adding some bases. Bases do the similar thing, you know, as acids. I didn't really talk about them yet, but I'll talk about them soon. But what happens if I perturb this? Now, you remember Le Chatelier's principle, right? Now, Le Chatelier's principle says if I dump in a whole bunch of acid in here, what am I dumping in? A whole bunch of hydronium. And so if I dump in a whole bunch of hydronium in here, is this still going to stay like this? No. It should shift to the left. Yeah. So let's try that. Well, let's put in an acid in here. Let's add some HCl. What molarity do I want to put in here? Let's go with 0.100 molar. This is a very common molarity that we use a lot. 100 molar HCl in water. And so I got this thing happening with water. And so here, we've got two approaches here. We've got the Le Chatelier's, or we have the reset initial. This is much easier. This is much more difficult. But we'll do it to show, because and so we got this equilibrium happening here. This. So initial, I have 1.0 times 10 to the minus 7 molar, 1.0 times 10 to the minus 7 molar. And so this is initial at equilibrium, right? We know that's at equilibrium. And then we add some HCl. When we add, HCl is a strong electrolyte, right? Strong electrolyte is going to be dissociated into ions. And so essentially when we add the 0.100 molar HCl, we're, well actually, this is 0.100 molar HCl. Ignore solution dilution. In other words, you know, when we add solutions together, when you mix two solutions together, you always have to worry about solution dilution, right? Because if you add 0.100 molar to water, water is going to dilute it, and your molarity should change, but we're going to ignore it. We're going to say we're going to add the HCl such that it stays 0.100 molar to make our life easier. And so we add that. And so we're going to add 0.100 molar here. It's going to perturb it. Now I'm going to get new initials. My new initial is going to be 0.100. That's 3, 4, 5, 6, 1, 0. Actually, I'm not allowed that many sig figs. I need to subscript them. So 0.100, that's significant. 1, 2, 3, 4, 5, 6, 1 molar. Okay, which way? Now this is my new initial. I have too too much product, it's got to shift to the left. So the change is minus x molar, minus x molar. And so at equilibrium, I'm going to reestablish a new equilibrium, 0.100 sub 0001 minus x molar 1.0 times 10 to the minus 7 minus x. And then solve for x. Using kW. This is a number you have to memorize. kW is equal to 1.0 times 10 to the minus 14. This Le Chatelier's approach, basically we aren't going to do any problems like this. Because it's much easier just to reset. Etc. Okay, try reset instead. You'll see it's much easier. What we're going to do is we're just going to pretend none of the water has collided. So we push all the water molecules to the left. Initial from water. 0 molar, 0 molar. Right? And so we reset the water equilibrium to the left. And then the initial from the HCl. The initial from the HCl, we have 0.100 molar. And 0 molar. HCl doesn't contribute any hydroxide, does it? No. Okay, now we have our combined initial. This is going to be 0.100 molar and 0 molar here. Which way is this reset initial conditions going to go? What direction is the change going to be? Is it going to be minus minus or plus plus? It's got to be plus plus. We've got a 0 here. Plus x molar, plus x molar. And so at equilibrium, I get 0.100 plus x and x molar. And so the advantage to this is I get one less binomial. But that isn't the only advantage to this. There's another advantage to this. Oops, I didn't quite catch that last part there. Which you'll see in just a second. I'll show you the other advantage to this. So maybe I'll write it over here because the camera doesn't quite catch that over there. This is the other advantage to this. When we set up the kW, kW is going to be the hydronium times the hydroxide at equilibrium. As we saw earlier, 0.100 plus x times x. Now, look at that K value. Do you expect much forward reaction to occur? K is 1.0 times 10 to the minus 14. 10 to the minus 14 tells you it's all reactant, so very little product should form. In fact, you know, if I start out with 0.100 here, is that a large amount of hydronium? I think so, compared to 10 to the minus 7. That's a huge amount, isn't it? And x, what do you think x is going to be like? Very small. In fact, do you expect x to be about 10 to the minus 7? Exactly equal to 10 to the minus 7? More than 10 to the minus 7? Or less than 10 to the minus 7 molar? Less is right. You know, in fact, I expect it to be a lot less. Why?
There's not much of it.
Okay. The way I like to think is if there's no 0.100 here, then these things have to multiply out to 10 to the minus 14, right? But now I have a 0.100 here, and it has to multiply to 10 to the minus 14, so I already have a huge amount here, therefore x has got to be even smaller, and a heck of a lot smaller, because I already got a lot of hydronium here. I don't need much more hydronium to get this equilibrium happening. And so in other words, this is the way I like to think about this, you know? The waters are trying to react here, right? But, you know, all of a sudden you have lots of predators around. And these predators are going to be the hydronium. And so as the water tries to form more and more hydroxide, what happens? The predators, the hydronium, come and attack the hydroxide, neutralizing it and going back to water, right? Now that I have a huge concentration of hydronium, am I going to build up much prey, the hydroxide? No, even though the collisions, can I stop the water collisions from happening? No, the water collisions are still happening at the same rate. I'm still producing hydroxide at the same rate as I was before because it's at 25 degrees C. The only difference now is now I have a whole bunch of hydroniums, and every time that the hydroxide is being produced, it's being consumed by the hydroniums, and I just can't build up much of a concentration of that. And so the collisions are proceeding as before. It's just, I got this big concentration here. It's going to prevent these from getting very big. Does that make sense? And so this is how we think about our dynamic equilibrium here. And so x has got to be a lot smaller, and therefore the other advantage of resetting is this. I could use the simplifying assumption. Whereas in the previous setup, could I have used the simplifying assumption? No, it would have been impossible in the previous setup because why? Yeah, if you ignore the x, then there's nothing left to solve for. You can't solve for x if there's no x, right? And so here it's very important. Right? It's very important that that you see, okay, the simplifying assumption should probably work here. That x is going to be much smaller than 0.100, which means this parentheses simplifies into what? 0.100. And now we can solve for x. Do you see how much time you save? I mean, if you had to do the quadratic equation by hand, you just saved yourself a lot of time. If you don't have to do the quadratic equation by hand, then maybe it's not that much time saved. But let's see how well it works in this case, because you know, I think it's going to work great in this case. I really do. And so let's take a look. X is going to equal, this is 10 to the minus 1. So this is 1.0 times 10 to the minus 13. Okay, then we do our double check. Actually, let's go ahead and calculate our concentration. So this is going to be 0.100 plus 1.0 times 10 to the minus 13. And so 0.100 plus, okay, 10 to the minus 13, I'm going to need 12 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then a 1, 0. And so did I add much? No. I certainly didn't. And so this is going to come out to 0.100 sub 0, 0, 0, 0, 0, 0, 0, 0, 0, 1 molar. Did I get the number right number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep. So this is really like adding a drop of water to a lake or something like that. It's not really going to change things much. How about here? Can I ignore it over here and just call it 0? No, because this is significant because I got 0 plus this, and so that is a significant change. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros after the decimal and 1 0 molar. Let's do our double check. Can somebody multiply out the K? When we check our answer, K is equal to what is it?
1.0
1.0
times 10.
1.00
My calculator just showed 1.
1.
Right up to 1.
All right, times 10 to the negative 14. So we're good. If you use the quadratic, do you think actually, if you use the quadratic, you know what? You get the same answer. Exact same answer. And so here, you know, the simplifying assumption works so well that it would have given you the same answer as the quadratic formula. Because, what do you think percent? You know, I forgot to calculate. I forgot to justify this.
5%.
What is the percent change?
Very.
Yeah, it's going to be very, very small. The percent change is like this. The change was 10 to the minus 13. The initial was 10 to the minus 1 times 100%. So this is going to be 10 to the minus 12, 10 to the minus 10. 10 to the minus 10% change is nothing. You know, this is fine. This is good. And so we expect it to work well. And so, do you see the difference? In Le Chatelier's, you would have definitely done the quadratic formula. Here, we didn't have to do it. And so resetting is the way to go, and resetting is the way to go for pretty much all these problems in this chapter. Did that change the pH much? We call this. The first part, well, let's look at some more examples. All right, so what we do here is this, the steps. Let me break it down. When we're dealing with more than one equilibrium, we try to do this in a stepwise fashion. All right. Let me just try to just do it stepwise. Step 1, start with the biggest K. I skipped this. I skipped this because we did it in our head. But starting with the biggest K is this. HCl plus H2O liquid goes to H3O plus Cl minus. K for this, when we look it up in the book or on the table, it's very large. And so this is just hydrolysis or ionization of water. And take a look at the acid chart over here. And then C. Can you see water up there? I mean, not water, HCl up there?
Yeah.
Yeah. And then on the right-hand column is the Ka. Well, Ka. A stands for acid dissociation constant. And what does it say? Well, it's blank, but go up or down, you'll see very large or large. And so we'll just call it very large. What does very large mean? Very large means we're just going to dissociate it 100%. I mean, how are we going to use a number for this? And so the way I should have done this is 0.100 molar, 0 molar, and 0 molar. We assume nothing's happened. And the change is going to be complete. The change is going to be complete because the K is very large. So, at equilibrium, how many HCl molecules do I have left? None. And they've all been ionized or hydrolyzed to hydronium and chlorine. And then we'll go to step 2. Step 2 is the next biggest K. The next biggest K is the H2O liquid plus H2O liquid. And it's quite a bit smaller. You know, we got the hydronium plus the hydroxide. And what we see is step 1, you know, does the chloride perturb or interact with this next equilibrium? No. The chloride stops here. And so we're left with 0.100 molar chloride. But the hydronium doesn't stop there because the hydronium participates in the next step here. And so what we do is we take this out of here and bring it over here. And so this is 0.100 molar. From the HCl. And how much hydroxide do we get? 0, because we're assuming that no water molecules have yet collided. The reason we're doing this is to make our math easier. Obviously, the collisions are happening all the time, so minus x, I mean, not minus, it's got to go plus because we got a 0 here. Plus x molar, and so we got 0.100 plus x molar and x molar. And then where we left off in that last one. And so this is the basic approach. Now, if we're interested in pH, you know, pH equals the negative log of the total hydronium in solution. It doesn't matter what the source of hydronium is. The pH doesn't care if that hydronium came from water or if it came from HCl. Right? It's just interested in the total. And the total hydronium in this case is the negative log of the hydronium from the HCl plus the hydronium from the water, H2O. And so we see that here. The hydronium from the HCl is this one, right? The hydronium from the water is X. So did X contribute much hydronium? No. X didn't contribute much hydronium. In fact, this is why in Chem 4, if you had pH calculations in Chem 4 or Introchem, you completely ignore the water. Because most of the hydronium in acid solution is going to come from HCl. And so when we calculate the pH of 0.100 molar HCl solution, we just plug in 0.100 molar as the hydronium ion concentration and don't even worry about water, right? Have you done pH calculations before or not? No?
Chem 4.
In Chem 4? Okay. So we can make a assumption that water is a negligible contributor to hydronium in acid solutions, and just ignore it completely, right? We'll continue on our way. But whenever you do those assumptions, you have to realize, or at least state, what your assumption is. Because a lot of people do that and forget. And so I want to do this one. 1.0 times 10 to the minus 8 molar HCl. I can do that. What is the pH of this? Well, you know, the pH is easy. pH is equal to the negative log of the hydronium ion concentration. So go ahead and figure out, what is the hydronium ion concentration? And tell me what the pH of this is. 8? Well, pH is going to be 8, but this is not significant. How many sig figs do we have?
2.
We have 2 sig figs, and so it's 8.00. Which is 8. Yeah, a lot of Chem 4 students will be able to do this in their head, right? pH is just the power of the hydronium ion concentration, the negative power of the hydronium ion concentration, which is 8. And then you would ask the Chem 4 student, wow, and so how acidic is my HCl solution? And then they would say, it's not very acidic because it's actually basic. Right. And so my HCl solution is actually a base. And then they would either accept that answer as okay or realize that there's something seriously wrong. Because is HCl an acid or is it a base? It's an acid. So how can you put acid into water and get a basic solution? And then the Chem 4 student wouldn't be able to answer this, right? They would have no idea what just happened because they were just broadsided by a semi-truck, right? Because what would they say? They'd have no idea. But fortunately, you Chem 1B students would know, right? And so what would you Chem 1B students say? Oh, it's too, yeah, that is neutral. 8, pH 8 and 7 are neutral. Both 7 and 8, and maybe a little bit above 8 are neutral. What did you say? I mean, it's close to neutral. pH 8 is close to neutral, but it's on the basic side of neutral. What would you say as a Chem 1B student that, I mean, this is weird because you're adding acid to water and you're getting a base. Doesn't make sense. You'd say, oh, it's due to experimental error. Right? Yeah, there must have been some kind of contamination. The nice thing about Chem 4 is you don't have to talk about this, right? We don't talk about these kind of things in Chem 4 because it's too much, and hopefully they'll never encounter this problem. But if they do, then they're going to be broadsided by a semi-truck, basically, because they're not going to have an answer, unfortunately. So this is why we're doing it in Chem 1B, so that at least you have some kind of answer. And so what is the answer?
The hydroxide levels are higher because when the acids are water.
It's very diluted acid at a very low temperature.
We're only looking at the hydronium ions instead of the
We're only looking at the concentration of the HCl.
Yeah. Versus what?
versus the H2O.
Yeah, right. See, the problem is we automatically made the assumption that H2O doesn't impact pH. But does H2O impact the pH? Yes, it does. And so the problem here is we didn't factor in the hydronium ion contribution from water, which we need to do. This is only the hydronium ion concentration from, and so this is impossible, basically. We can't not add acid and get a base solution. I mean, that's all we're adding to water. And so this is our Chem 1B approach to, first we want to do this stepwise if possible. It turns out not everything we can do stepwise. And so, but stepwise is the most common, like 90% of the problems we'll be doing stepwise. Stepwise meaning we start off in step 1 with the biggest K. The biggest K is going to be HCl. And a lot of people skip this step. Our book skips this step because everybody should be able to do this in their head. You're going to produce hydronium. Everybody knows how much hydronium this is going to produce. So it should be 1.0 times 10 to the minus 8. But I do it because we're doing all the problems the same way, using the same method. And we just reset everything and then start from the beginning, assuming nothing's reacted, and then just let each step react the way it should react. We know that Ka, A stands for acid or acid dissociation constant. Ka is very large. A very large Ka means we just go to completion. This is going to be minus 1.0 times 10 to the minus 8 molar. It's going to be plus 1.0 times 10 to the minus 8 molar. Plus 1.0 times 10 to the minus 8 molar. And so at equilibrium, how much HCl do I have left over? 0. 1.0 times 10 to the minus 8 molar. 1.0 times 10 to the minus 8 molar. Now we don't stop here because there's another equilibrium happening, right? What is the other equilibrium happening? Water. So step 2, you're going to look at water's equilibrium, H2O liquid plus H2O liquid. It's going to give us hydronium plus hydroxide. And the way we do this is we just automatically reset. We just assume that none of the water has yet reacted, but there is some hydronium present. The hydronium is coming from the HCl step 1. Chloride's at the end of the line, so nothing's going to change for chloride, but hydronium could change. So we got 1.0 times 10 to the minus 8 molar, and 0 molar. There's no waters collided yet to produce hydronium and hydroxide. And so the change is going to be plus plus or minus minus? Yeah, plus X molar, plus X molar. And at equilibrium, we expect 1.0 times 10 to the minus 8 plus X molar and X molar here. Now, let's go ahead and try to solve for X. So Kw, you memorize 1.0 times 10 to the minus 14, which is equal to the hydronium ion concentration at equilibrium times the hydroxide ion concentration at equilibrium. And then plugging in the numbers over here, we're going to get this. This is going to equal 1.0 times 10 to the minus 8 plus X times X. This is a great candidate for the simplifying assumption. So let's go ahead and use the simplifying assumption here. SA. We use the SA, we're going to get 1.0 times 10 to the minus 8 times X. In other words, X should be much smaller than 1.0 times 10 to the minus 8. Why do I think it should work well here? Because K is very small. K is very small. Well, let's see. And so if we do that, x is going to equal 1.0 times 10 to the minus 6. And then I do my percent change. And so I'll put the change, which is 10 to the minus 6, over the initial, which is 10 to the minus 8 times 100. Then, which means it's a 10 squared times 10 squared is just 10,000% change. Is that okay? No. Why didn't it work here? It should have worked here, but it didn't work here. Why? The assumption is obviously wrong, but why did it work in the last problem and it failed in this problem? Even though the K value didn't change. The K value is the same as the last problem, but it worked in the last problem, it failed in this problem because? Yes, right. In the last problem, we had a huge amount of hydronium to start with. In this problem, we have a minuscule amount of hydronium. And so it's like 1 drop compared to a lake is nothing, but 1 drop compared to 1 milliliter is something, or half a milliliter. You know, if you take 1 drop out of a half a milliliter, it's significant change. Because a half a milliliter consists of just 10 drops. So it's a 10% change. And so it's because my initial, the initial is small. And so your book says this. What you do to get an idea is you might try this. To get an idea of where K is likely to work. K is likely to work, I mean not K, SA is likely to work, when the K to initial is greater than, say, 1,000. Something like that. This is very rough. You know. Oops. I did it. I'm sorry, I did it upside down. Let me change that. The initial over K, we want a small k and a big initial, right? Small k, big initial, let's say greater than 1,000. Then it's like it. So let's do that here. You know, when we looked at our initial, 10 to the minus 8, and the k 10 to the minus 14, maybe I had it right earlier. Did I have it right earlier? Yeah, shoot. We want small k and a big initial. Yeah, I guess this is right. But it should have worked, huh? Well, this is just guideline. Guideline. I think the book might be 10,000, but I don't really use that. I don't really use this because I just try it. It doesn't take much time to try it. After you do a bunch of these, then you'll get an idea of what should work or what shouldn't work. So it failed, so we can't use it. And so what do we have to do? Unfortunately, we have to do the quadratic equation. And so when you're doing the quadratic equation, it's going to be x squared plus 1.0 times 10 to the minus 8x minus 1.0 times 10 to the minus 14 is equal to 0. And so x is equal to what? 9.51 times 9.51 times 10 to the minus 8. Thank you. Okay, so let's go ahead and calculate this. This is going to be 1.0 times 10 to the minus 8 plus 9.51 times 10 to the minus 8, which gives me 10.51 times 10 to the minus 8 molar. So in other words, this is the hydronium from the acid. This is the hydronium from the water. This is the total hydronium. So out of the total hydronium, about what percent came from the acid and about what percent came from the water? Yeah. So we'll just keep it simple. About 10% came from the acid and 90% came from the water. Something like that. Actually, more than 90%. More than 90% of the hydronium came from water. Why? Because we had so little acid in there. Would you drink this? You know? I'll drink this if you pay me $10, I'll drink this acid solution. 1 times 10 to the minus 8 molar. I'll drink it, no problem. Yeah, actually anybody would drink this because for $10, I mean, what is the pH of this? Well, go ahead and calculate it. Now we can calculate. The pH is negative log of the total hydronium. Now we have the total hydronium. And it's negative log of 10.5 times 10 to the minus 8, which gives me 6.9. We're allowed 3 sig figs, so 6.978. Give me one more. 4. It's not rounded, is it?
It rounded.
Don't round it.
Also 3.
6.9783. I mean, think about the water. When you drink the water from here, what's the pH? Like 5. Okay, the difference between pH 7 and pH 5 is 2 orders of magnitude. So it's 100 times more acid in this than this. So you're already drinking way more acidic water if you're drinking from the tap. And even if you're drinking bottled water, well, bottled water, you know, they can make it alkaline or they can make it acidic. Depends. But anyway, this is close to pure water. I'd have no problem drinking this, even if nobody paid me to drink it. But that always, you know, my high school, when I was taking high school chemistry, my high school chemistry teacher always said, you know, when you mix acid and water, you get salt and water. And so he always said, oh, I'll drink it, but he never did drink it after doing it. So I was always waiting for him to drink the product and the acid-base neutralization. All right. Anyway, this is incredibly dilute. And so when the point is, when is it? Because to do this extra step takes time. Step 2, right? And sometimes it's necessary, like this problem. Sometimes it's not necessary. Like the last problem, if we skipped step 2, would that have changed the pH? No. In the last problem, you know, without step 2, we got 0.100. With step 2, we got 0.100. That's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We added that much? Does that much extra hydronium make any difference? No. And so here we could have saved time if we just skipped step 2. But when we try to skip step 2 in this next problem here, this one we just did, it failed. And so when do we worry about hydronium from water? Right. We worry about hydronium. What's the maximum amount of hydronium we're going to get from water? It's going to be when it's pure. In pure water, the maximum amount of hydronium we're going to get is 10 to the minus 7 molar at 25 degrees C, correct? And so if we have hydronium in there to begin with, then we're going to get less because the hydronium is going to act as a predator for the hydroxide and prevent the hydronium and hydroxide concentration from water from getting too high. And so when we worry about it is we would worry about step 2 if the initial hydronium were on the order of 10 to the minus 7, 10 to the minus 8, 10 to the minus 9 for sure. We're going to worry about it. And if we had 10 to the minus 9 molar, then more than 90% of the hydronium is coming from, way more than 90% is coming from water. And so we start to worry about it like 10 to the minus 6, 10 to the minus 7, 10 to the minus 8, 10 to the minus 9. But if we're at 10 to the minus 5, and I'm going to add at the most 10 to the minus 7, 10 to the minus 8 maybe, 10 to the minus 8, 10 to the minus 9. So if I had 10 to the minus 5 with an addition of 10 to the minus 8, make any impact on it, really? Not really, not the 2 sig figs, you know. And so, there's a judgment call there. One to worry about it. And so typically what people do is they always do it. You always do it because, you learn by experience, right? And so if somebody tells you, okay, everybody wants a simple rule. Tell me what to do, tell me how to do this. So they want a simple rule saying, okay, do step 2 when this happens, right? And so you follow that, but you don't know, you don't know that rule very well. You don't know how that rule is based because somebody just told you, just follow this rule, right? And so this is what scientists do. The best way to do this is just to do step 2. You always do step 2, and then pretty soon you'll develop the rule because you'll have done enough of these so that you can see a pattern. And when you see the pattern, then you can make a judgment. It's the same thing with this ridiculous rule, this initial over K. And people want to follow this to the letter, but it doesn't always work, because it's just a simple rule that, and you don't know the nuances to the rule because you haven't done enough of these, And so what you do is you do a whole bunch of these and look, what was the initial over the K or what was the K over the initial ratio? And then see how well it works or how it failed. And then pretty soon you can develop the rule for yourself, and that's a much more meaningful rule than following somebody else's rule. And so normally the way I do these problems is I don't skip any of the steps. I do all the steps. Now that's different than Petrucci because Petrucci, if you look at the solutions guide, he'll skip them. He'll skip a lot of steps because, and then a lot of students say, why did you skip that step? Well, you can skip that step, right? But, what I recommend is don't skip any steps. The solutions guide is going to skip steps because those people have a lot of experience doing these types of calculations, but you should always do it systematically in the same method that we're doing here, step 1 and then step 2. And so why don't you try this as an example. Just, these calculations shouldn't take long. 0.100 molar sodium hydroxide AQ and 0.100 molar, not 0.100 molar, sorry, 1.0 times 10 to the minus 8 molar sodium hydroxide. Those are just the same type of problem, except rather than looking at hydronium, we're looking at hydroxide. The same type of thing is going to happen in these problems. And so we end at what, 55? Okay, so we're done for today.